organizer of this seminar, who sometimes also is a speaker.
Okay, thank you, Dr. Z, for the introduction. So my title of my talk is something along the lines of conjecturing new partition identities with computer algebra. That's what's on my notes. So let me just start off with a bit of preface for those of you who were around last week for Shashank's talk. So our talks are going to be somewhat similar. They're going to have much of the same initial information. So there will be some overlap at the initial stuff just because we need to make sure that the talks are completely self-contained, but they will diverge at the end. So just as a basic comparison between the two talks, Shashank's talk last week was work that was providing new proofs of already known identities. There was some computer work that went on in actually coming up with in constructing the way to prove those identities. So today's talk is actually going to be more on just the conjecture side of things rather than the proof side of things. So this is just going to be stuff that as we'll see at the end, it's just going to end up being some conjectures left at the end, maybe some ideas of how to prove them, but no actual proofs, but more on the experimental side of things. Okay, so just with that in mind, hopefully, again, apologize for having to go through the same backdrop information 2 weeks in a row, but any luck after we've gone through this, and with those of you who've also sat through the GCS Graduate Combinatorics Seminar a week ago, you will be quite good at partitions by the end of this. That is the goal. So we will see how that comes out. Okay, so we're talking about partitions. So it's a finite, non-increasing sequence of positive integers, such that lambda 1 plus lambda 2 plus lambda k equals n, partition of n. And so, for example, we can, how many partitions of 5 are there, just as a reminder? So we can do 5, we can do 4 plus 1, we can do 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and all ones. And so we can ask questions, how many for any given integer n, how many partitions of n are there? And that's a good question to ask. Been studying a long time. And so here we can see that p of 5 is 7. But we don't have to just stop there. That's only one question. We want to ask lots of interesting questions. And so we can do this with various restrictions. So
Maybe you should mention the A number. What's the A number of this one?
Yeah, it's, what is it, A41.
Okay.
Okay, there we go.
The A number.
Yes. We will certainly be coming back and using OAS later on in the talk, time permitting. Okay, so back to this. What restrictions can we have? And so we can consider partitions where only certain things are allowed to happen. So, for example, only certain parts, i.e. odd parts. So that's one sort of restriction. So you can, so instead of being able to use any integer you want, you can only use odd integers, or come up with some other set S and just say you can only use the integers in S. And so that makes for a perfectly good restriction. There can also be restrictions on how parts interact with each other. And so an example here, that's an e.g., not e. I want to go straight. Okay, e.g. Distinct. And so what I mean by here is that there's distinct parts. You're not allowed to use any part more than once. And so that is an example of parts interacting with one another. So if you put, say, a part of 5 into your partition, it bumps out the other 5s. It kind of occupies that slot, fills up its room and makes it so that nothing else can get in there. And so these are two restrictions, very, very common restrictions, and as we'll see, these are kind of the most basic restrictions that they're very representative for big classes of restrictions. And so let's take a look to see back over here, odd parts and distinct parts and stuff like that. So 5. So 5 is, circle the ones that are into only odd parts. So this is, 5 is only part here and it's certainly odd. Even part here, so those don't count. There is an only odds, and there is only odds. So there are 3 partitions only using odds, and maybe some different colored chalk will do the trick here. For distinct parts, so that is also into distinct parts. That is also into distinct parts, and that is into distinct parts. And so here we can see that, and you can check for yourself, and then the others are into distinct parts. So there are 3 partitions of 5 into odd parts, 3 partitions of 5 into distinct parts, and lo and behold, that is not a coincidence, that is always true. So this goes back to Euler. Hopefully Nathan is no longer quite surprised by this after hearing this so many times. For all positive integers n, the number of partitions of n into odd parts equals number into distinct parts. Okay, so that is our, I guess, prototype or our main example. What sort of theorems that we're going to be looking at, and so we can generalize this. Okay, so let's think about generalizing the odd parts, and so that side of things, we're going to have a special name for them. So they're called product sides. So what do I mean? So I'm going to kind of turn this into a technical term. So when I say product side, I just mean partitions into parts that satisfy a congruence condition. And so here, the generating function turns out to be a snap to write down. So I'm not going to discuss this, but it's easy enough to see that. So if I do this, I guess I don't really need the parentheses. So if I do this generating function, this is the generating function for all partitions, no restrictions whatsoever. So each term m here just corresponds. So each factor with 1 over 1 minus k to the m. This corresponds to allowing the part m in our partition, where it can appear as many times as we want. And so I want to say satisfy congruence condition. I'm just going to be lazy here. I'm just going to say, okay, m satisfies congruences. So this might be a way that, now I have a product side. And so hopefully we can see it is, we call this the product side because it is written as a product here. So just as an example or two, so we might do something m greater than or equal to 1, and m is congruent to 1. mod 2. So that is a perfectly good product side, and in fact that is exactly the product side that we have over there. So now we want to talk about the sum sides. So this will be another term to introduce here. And so this is so these sum sides. These are going to be counting up partitions that satisfy certain conditions about how the parts interact with one another. When we say just a bit of notation here, or terminology. So we call this the sum type because sometimes we are able to end up getting actual, yes, Nathan spotted that pun there, that was unintentional. Yes. Sometimes we get analytic infinite sums. But we can't always explicitly write down analytic sums, analytic series for them, but it doesn't matter, still convention, we refer to these as sum sides. So, okay, we have distinct parts. So when we say distinct parts, that's really a statement about how far apart the parts have to be. So basically, it's saying that any two, so distinct parts is equivalent to saying any two consecutive parts in our partition have to differ by at least one. So we can start to think about how to generalize this. So just as in this odd parts business can be generalized by writing down any sort of congruence conditions we want. We can usually just erase this and say n is now congruent to plus or minus 1 mod 5, and that's a new product. All we have to do is erase that. We can generalize this, distinct parts being difference 1 at distance 1 to being difference d at distance k. And so what this is saying is for all j, lambda j minus lambda j plus k is at least d. And so Euler is just using 1 and 1 here, making distinct parts.
So you've ordered the lambdas.
So yes, I probably should have written that up there. This will. So we traditionally write ours in, and this is a very important point here. Okay, so I should have said something to that effect at the start. So our partitions, yes, they are in order. We always write them in decrease or at least in non-increasing order, and they all have to be positive. So yes, that does allow us to make statements about this. That they are in the order that we want them to be. Okay, good question. So let me just wrap up the sum sides thing, because we can start, kind of coming up with what other things are appropriate to look at. And this one won't, might not be obvious now, but hopefully we'll see this come up. Is what we will call initial conditions. And so initial conditions are kind of like, what sort of behavior do you have kind of down here when the parts get close to 0? Is there something funny going on? And so one sort of thing that we could put in here is minimum size of smallest part. And then how often this part is allowed to appear. So you could say minimum, the smallest part, which means all parts, have to be at least 2. That would be a perfectly reasonable thing to say. You could say something like, not only, so smallest part has to be at least 2, and it can appear at most once. that is also a perfectly legit thing to say. And we'll see that that people can form identities using this framework. So, clear so far? Any questions before we move on to kind of the next part of the talk?
Well, I have a question.
Yeah.
Suppose you didn't want it to hold for all n,
Yeah.
but you could relax that condition. It should only hold for certain values of n.
Ooh,
Has anyone ever looked at that?
I don't know anything like that. That feels dangerous. That's like, are you allowed to do that? but certainly something interesting to think about. Okay, so this is kind of all the prelim stuff. So now let's talk about what's been known. And so let me just restate Euler for good measure. So I'll just say 1700s or so. And so here, so any single one of these identities I can write down, I can just kind of classify them. I can describe them really simply in this form. So Euler, I can just say the product side is 1 mod 2, and when I say that, just to write this instead. And then when I say the sum side is difference 1, distance 1, so just use this. And then there's no initial conditions on this. So there is an elegant generating function proof of this. That is the sort of thing that I think I put on my combinatorics final over the summer for my students. There's also a bijective proof, which is very, very nice, that I believe is due to Glacier, I want to say. Glacier usually does those sort of bijective proofs. So that wasn't until much, much later. But it's like proving the identities isn't really the main point of the talk. This is more of an experimental talk. And so basically what we're doing right now is kind of coming up with, we're trying to see like what parameters could we tweak here.
Can I make a philosophical?
Yeah, please.
Okay. You have complete proofs, but not mathematical proofs.
Sure.
You have empirical proofs.
Yes.
That's proof for me.
Yes.
But not a mathematical proof.
Yes. So this is 1700s or so. And so then the next one, there's a reason I put up plus or minus 1 mod 5. So this is Rogers-Ramanujan. Let me write out Ramanujan. So there are 2 identities here. So I can again just kind of write them in notation. Say the product side is plus or minus 1 mod 5, and then the sum side is difference 1 at distance 2. So
Difference 2.
Reverse.
Oh. Yes. My mind's on autopilot. I'm not actually thinking about what I'm saying or writing, so that looks much better. And so this is now, again, the parts are interacting with each other. If you stick a 5 in your partition, not only does that bump out any other 5s from joining your partition, but it also bumps out 4s and 6s from joining your partition as well. The second one is again a mod 5 one, and the sum side is difference 2, I'll get that right this time, at distance 1. And also smallest part at least 2. So you're not allowed to use 1 at all. So, yeah, question?
Can you explain the first part? I just...
You say the first part, like this up here?
No, the Euler part.
Oh, the Euler part?
Yeah.
Okay, so what Euler is saying is that, so these are all identities. It's of the form a product side equals a sum side.
Yes.
And so the product side here is parts congruent to 1 mod 2. So use this and make that 1 mod 2.
Consider coefficient with q to the power of 6. So there are 3 diagrams, like 6, 5, 1, and 3, 3.
Okay, so So 6, 5, 1, 3, 3. That are into. Okay, so those are distinct. No, what is it? Sorry. What?
Maybe I just didn't get what the.
So let's work out. Yeah. So we can certainly work out.
No, I can say that.
Yeah. We can certainly work out partitions of 6. So 6, 5, 1, 4 plus 2, 4 plus 1 plus 1, 3 plus 3, 3 plus 2 plus 1, 3 plus 1 plus 1 plus 1. So that takes care of 2 plus 2 plus 2. Okay, so these are our partitions of all of 6. And let me just once again, so let's see. So distinct parts. So let's see. I think those are all the partitions into distinct parts. There's 4 partitions into distinct parts. So that's our sum side, difference 1 and distance 1. All the others violate that in some place. And then for the odd parts, let me just put star 1, 2, 3, 4. So these might end up being different partitions that you end up with, but the point is you always have the same number.
Oh.
So
the number.
Yeah. So certainly there, we are not making a statement that you get the exact same partition, but you get the same number. As I said, there is an elegant bijective proof that you can quickly go from those 4 to the other 4 and vice versa. Although, kind of an interesting thing down the road is that we'll see, for example, Rogers-Ramanujan does not have a elegant bijective proof, which is kind of, so then it's kind of like we have to think about, we just have to do proofs that are just verifications, as Hardy said. All of the proofs of Rogers-Ramanujan, in his lifetime, according to him, were merely verifications.
Well,
Yes. So that's why I said that in his lifetime, all of the proofs up to that point were verification. There certainly been interesting discoveries by some people in the room that connecting them up to Lie theory and stuff like that do shed some light on what's going on. Okay, so we got Euler, we got Rogers-Ramanujan, so we're starting to play around with this list a bit. So far we've seen distance 1 in both our cases. The difference is starting to get a little bit interesting. But then next up we've got, the question is, will we ever see this? We ever see the distance change? And in fact, we do here. And so the next up is it was thought. So Rogers-Ramanujan, which is now disappeared up there. Rogers first came up with it in the mid 1890s or so. Nobody read the paper. Ramanujan rediscovered it, and he found Rogers, and they provide a new proof of it. Eventually, I think McMahon came up with a combinatorial interpretation. When they first wrote this down, they didn't have the partition theorem.
Yeah, one only had an identity that implied.
Right. Yes, exactly. And so things kind of wrapped up about 1920, and then nobody came up with new. Well, I guess Schur had his identity at one point, but the question is, where are new identities? And I think that somebody in about 1950 or so said we have found all the partition identities we are ever going to find, sort of thing, and had some argument for that. And the thing is, it's actually turned out, thankfully that was wrong. Maybe he just wasn't considering the right types. It's always interesting. We're trying to generalize these in that you have to come up with the correct way to generalize them. So the thing is that when you look at Rogers-Ramanujan on first glance, you look at it and you say, okay, how do I generalize like the product side? And it's like, oh, I'm looking for identities that you're allowing exactly two congruence classes mod something. Maybe that's what I'm looking for. And that turns out to not be the way to generalize it. You're not including two of them, you're excluding three of them. And so, that's on the first glance, why are you saying that? That's just equivalent. But it turns out we're not looking to generalize including two of them, we're looking to generalize excluding three of them. And so now we have Asa Gordon he was at UCLA for a long time. This work is maybe about 1960 or so. And so his product sides were not congruent to 0 or plus or minus I mod 2k plus 1. And so so he has one identity here for each I from 1 to k. And then his sum side, so you can see we are excluding 1, 2, 3 things, mod an odd integer. His sum side was difference 2 at distance k minus 1. So now you actually can use the same part more than one. Before, like we were forbidding you from using the same part more than once. Now you can use the same part a bunch of times, up to k minus 1 times. But then, or you can have some 5s and then some 6s, but you can't have more than k minus 1 5s and 6s combined. And then also there was a initial condition at most I minus 1 occurrences of 1. So that fits into our initial conditions. And this is a generalization of Rogers-Ramanujan. If you do set, I won't go into all the details, but you should realize that if you set k equals to 2, so k minus 1 is 1, for the distance, you do get the two Rogers-Ramanujan identities. Okay, so we have, okay, this is suggesting, this is a pretty good list of sum side conditions. And people, so Gordon's was 1960. Last week, Shashank talked about the Andrews-Bressoud identities, which came out into the 70s and up to about 1980, that are coming up with similar things, but this is an even number instead of odd number for the modulus. But now, the next one that we want to talk about is Capparelli. And so this one is actually due to Stefano Capparelli, who was a PhD student here under Professor Lepowski back in the and Wilson back in the late 80s. And so he came up with this conjecture that he ended up proving based off of his Lie theory work. And so here our product side, I can just write down really simply plus or minus 2, plus or minus 3, mod 12, and then our sum side is difference 2 at distance 1. So that is the same thing as Rogers-Ramanujan. Smallest part at least 2. So that's taking care of our initial condition. And then let me just give myself lots of room to write this. If consecutive parts are within 3 of each other, their sum must be a multiple of 3. And so all of a sudden, this is like, this kind of sticks out to you the first time you see this. If you're thinking that like these are the only conditions that we can stick on our sum side, it's like, oh, where does this come from? So we look here. So it's difference 2 at distance 1. So any 2 consecutive parts have to be at least 2 apart. But if they're either 2 or 3 apart, there still is you're not home free yet. You have to check the second condition that their sum ends up being 0 mod 3. And so this is suggestive of a third type of condition that we can stick on our sum sides. And so, let me just